So, welcome everybody to the TransferLab seminar of today. Our seminar is a platform where researchers and engineers share and discuss recent advances in AI and machine learning. And we work at TransferLab in topics like data evaluation, probabilistic modeling, simulation, and AI, and also reinforcement learning. And this is what we will have a talk today by Maximilian Hüttenrauch, who is AI researcher at the Applied AI Initiative. And he will give an kind of overview talk today about episode-based reinforcement learning using movement primitives.
Yeah, as you already mentioned, this will be like more of an overview talk today about episode-based reinforcement learning using movement primitives, where I will introduce at least the concepts, what movement primitives are, and also different learning settings for episode-based reinforcement learning, and also showcase some reinforcement learning algorithms from these domains. But I will not go into much details on how these problems are then like what's the actual like solving of these tasks, more like an overview. Also, I assume that you have some background knowledge at least of reinforcement learning, because I will not give like a fundamental reinforcement learning introduction. Having said that, at least I have like one overview slide, because I guess most people today are familiar with like deep reinforcement learning, because it's widely used in all kinds of sequential decision-making problems, and it works well in a very broad set of tasks. For example, like this usual like test bed or benchmark is these kind of Mujoko simulations. In this case, it's the hopper, where the task is that this one leg moves as fast forward as it can. And to give at least some details on it, like the state space of this hopper is like an 11-dimensional vector, and it consists of the three joint angles. So there's like three individual parts and the joint velocities and some other properties. But basically, like we will look at a lot of like joint positions and velocities today. And usually it's really like the step-based paradigm. So like we take an action, so we actuate all three joints in the torque space, so like acceleration space of this kind of robot. So based given like a current state, we take an action, and then like this whole cycle repeats. We get like a reward, and then in the end we want to optimize for the maximum reward. So for a policy that gives like the maximum reward. As I said, this actually works quite well. So the question is, why actually would we need something episode-based reinforcement learning? Well, at least I can give you two, I think, good reasons why thinking about other learning approaches is also necessary, at least in robotics. For example, the first one is, if we look at this plot here in blue, we can see the action or the mean action of the policy taken over time for one of the joints, basically. So in blue, it looks kind of nice and smooth. But if we look at the orange one, which is basically the exploration policy, so we have the mean plus minus or plus some noise that is sampled to the action, then we can see that it's actually kind of jerky. And while Mujoko characters don't really care about this, an actual robot might care about this, because it will break if we apply these kind of torques or actions to the system. And also, Otterdar showed that like learned policies using this kind of exploration noise actually lead to policies that are not so energy efficient. Another reason is that we cannot specify every task in a sense that it's like a meaningful step-based reward. For example, like in the previous example, we had that this hopper here was tasked to move forward. But what if we wanted to jump on top of a box, for example? So this means that the reward maybe is not dense in time, so it may be like a sparse reward. Only once at the end of the episode, we can clearly say, okay, it has landed on top of the box or it hasn't. And also the composition of the reward function might not be Markovian anymore. So that means we might have to look at the whole trajectory over this episode and see, for example, okay, what was the maximum height that the hopper reached, or what is the closest distance it ever reached to like the center of this box here. And all these kind of reward functions are not really suitable to be solved with like step-based deep reinforcement learning algorithms. So maybe to summarize again, what's the goal for this talk is to provide like a different approach to learn these kind of episodic tasks, especially in the domain of robotics. Before we start, I'd like to introduce this movement primitive concept, because I don't think many of you have heard of this before. Movement primitives are basically a way of parameterizing trajectories. So we have some function that gets some weight vector w, and it returns a trajectory. So, and a trajectory is basically a sequence of states, or in terms of robotics, a sequence of joint positions and joint velocities that describe the movement that the system should take over like a whole episode. So for example, in this example here on the top, there's a robot arm with like a maracas instrument here in its hand, and it's basically, it needs to like shake this up and down to play this instrument. What a trajectory, for example, for this joint here would look like is that it's like kind of like a sinusoidal movement over time. So it has to go down and up and down and up and down and up. And this function, or like, yeah, over time, is then based, this is the trajectory in joint space. And this is provided by a rather low dimensional parameter vector W. So based on the complexity of the movement, this can be like in the orders of 10 to 100 parameters that need, that specify like a trajectory. Movement primitives also have some other nice characteristics. So they can be given some demonstrations, they can be like blended or combined. And they're actually quite simple, because they only most of the time use like a linear basis function model as a function approximator. We will later on see some examples on this. The execution of the robot is then, so the movement primitive only provides the trajectory. It's not the actual controller of the system. So the controller is then something like a trajectory tracking controller, like a PD controller, that takes in the desired trajectory and or the desired joint position for the current time step, and also the actual joint position and velocity of the current time step, and then outputs a torque such that like this arrow between like the desired one and the actual one is minimized. So this is movement primitives as a concept. If you want to look at instances of movement primitives, so the first one that I want to show is the so-called probabilistic movement primitives. And what this is basically a distribution over trajectories. So given a mean that is parameterized by this linear combination of like this feature matrix phi and the weight vector w. And this feature function phi, you can actually imagine it quite simple. So this is a plot of this matrix. So it's basically, so if you can count them, it's like 11 of these basis functions, of these radial basis functions. And let's say it's the discretization in time of 100 time steps. So we have a 100 time steps times 11 matrix times an 11 dimensional vector w. And this then basically gives, for example, like this, depending on the weights in W, this can give like this bold trajectory, mean trajectory over time. And the covariance sigma then specifies, okay, like what's the variance around this mean trajectory. So it's actually quite simple. The trajectory is defined directly in terms of position. There's just one problem, like with this representation, the start position is not somehow built into this movement primitive representation. Then there's another kind of movement primitives. They're called dynamical movement primitives. They actually have this function built in because they are defined in terms of an acceleration profile instead of directly in the joint space or. And they are basically a spring damper second order dynamical system, which says like, okay, coming from like a start state, we want to be driven towards a goal state. But on this way, we want to be forced some away from it, because just going from smoothly from a point A to a point B usually doesn't solve a task. And this forcing function then again is like this linear basis function model. So if we, for example, look at this trajectory, we want to go from point 1 at time step 0 to point 0 in time step 100, but not on a like straight line, for example. We apply like this forcing function to actually force it away a bit, and then we end up at this point at time step 100. The last instance that I want to present is the probabilistic dynamic movement primitives, which basically combine the advantages of the pro-MPs and DMPs, because they are probabilistic, and they have this nice built-in property that starting conditions of the system can actually be enforced. And it's also nice because it's directly again in the joint position space. So we don't need like this like double integration to get from the acceleration space into the velocity space into the joint space. It's not like super important to understand like all the details. I think it's just important that you understand like this concept that a movement primitive provides a trajectory, and then that this trajectory basically is like a rather simple model of a linear combination between basis functions and a weight vector. So is this maybe clear so until now? If not, if I don't hear anything, I'll just continue. So maybe you guessed it already. So what actually defines the task, or like what solves the task, is W. And the question, of course, is how do we get this W? And like one easy approach, or one approach, is if we actually have good trajectories recorded from like examples of a task. So for example, if we had like this maracas playing robot, we can actually like move the arm, record the trajectory, and then take these trajectories and then doing like linear regression or least squares regression, we can actually obtain for each trajectory, we can obtain a weight vector W that describes the task. And in order to create a pro-MP out of this, we can, if we have multiple trajectories, we can adjust to maximum likelihood. And the mean trajectory is then the mean over, or the mean of the weights is then just like the empirical mean of the overall Ws and the empirical variance. And this basically then just describes the pro-MP. But of course, we don't always have demonstrations, and that's where we can use reinforcement learning to basically do it the other way around. So we have something, we have a reward function that describes the task, and we want to find a distribution pi, like some kind of a policy over these weight vectors that maximizes the return. The return in this case is then this defined as like this episodic return of the task. So given a weight vector, and the expectation is because maybe the execution is kind of noisy, or there's like some inherent noise in the environment. Maybe in a graphical way. So if blue is the reward function, then and our initial policy, like is for example like a Gaussian here, like this lighter shade in the back. So we have this we have a single parameter in this example. So the x-axis is basically just W. We can take samples of W, evaluate them on the reward function, and then we want to move our policy towards like the optimum of the reward function. In a sense, we have like a hierarchical problem that we solve. Like we first choose a W that describes the whole trajectory, where the mean of this distribution is our current best estimate of the maximum of the reward function, and the variance is the direction to explore actually. And the low-level policy is then this open loop controller, for example, a PD controller. If we want to go towards an actual algorithm, we can see that if it would just be optimizing this objective in an unconstrained way, we would basically like converge very early and don't get to an actual optimum. So one way to tackle like this exploitation trade-off is to introduce constraints between subsequent updates. So we have again like this the objective of maximizing like the return, but between like subsequent iterations, we want that the next policy is close to the old policy, and also that the entropy of the policy doesn't shrink too much. So again, graphically, we can see that if we don't have the constraints, we would just go towards our best estimate and the variance would shrink. And if we actually obey, or like if we have meaningful constraints, like then we can control that we go towards this optimum, but don't lose too much entropy on that one. So basically, this is then like a concept basically of like information theoretic policy updates. Information theoretic because we use like these notions from information theory, like the KL divergence and entropy. But in the end, it's just like a policy update that gives us a new policy that is the result of a constraint optimization problem. And one algorithm that solves this problem is the model-based relative entropy stochastic search algorithm, where the idea is to replace this return function with a learned model. And it's actually a quite like simple model because it's only like a quadratic in W. But choosing it this way actually gives some nice properties, because then we can solve the whole thing in closed form, because if we choose the pi to be a Gaussian, then this basically are the compatible features, and we can just solve everything in closed form. And an iterative algorithm would look like this. So we would estimate these parameters of this reward model from sampled returns, plug that into this optimization problem, solve using the method of Lagrange multipliers, and then we get update rules in terms of the optimal Lagrange multipliers. And this can everything be done in closed form. We just need some convex optimization to find these optimal Lagrange multipliers. And it's also quite a nice algorithm because the update direction is in direction of the natural gradient. To actually plug in some of my own work, we showed that it's actually more efficient and more stable to update for the mean and for the covariance independently by keeping the other parameters fixed to the old distribution. So coming back to this hopper jump example, so we have in the beginning like this starting condition, and in the end we want to land on top. And if we see in the bottom learning curves for different algorithms, so we have like these model-based, as a Morse, this algorithm that I just presented, then CMAS is just another black box optimizer, then two algorithms that also do some black box reinforcement learning, but based on a policy gradient objective, and then 3 step-based deep reinforcement algorithms. And we can actually see that when we look at the reward plot over the update iterations, that step-based deep reinforcement learning algorithms such as PPO, SACTs, we are not able to really solve this problem. Only algorithms that take like the whole episode into account are actually able to solve this kind of problem. So for example, in this table tennis example here, the context could be the initial ball configuration in terms of like the velocity vector where it's incoming, and a desired target position where the ball should land. And then our policy basically is still a Gaussian, but with like a parameterized mean. So the mean is actually a function then of the context, and also the covariance can be a function of the context. Again, we are optimizing for the policy that gives the best reward, where the reward now is not only dependent on the weight vector W, but also on the given context. Again, then an algorithm that solves this task is deep black box reinforcement learning by Otto et al. And here is actually a neural network that maps from this context to the distribution parameters. So if we have a look at this figure, so the environment provides us with some context, which, for example, like can be part of the state or like an image. Then the output of this contextual policy is then context-dependent mean and covariance. And then again, we sample weights. We create our trajectories, we execute the whole trajectory in the environment, and we are provided then the return of the episode, and use this return of the episode to define an advantage function, which is kind of similar to the step-based one. So the step-based advantage is a function of state and action, and here it's a function of context and weight vector. And then the objective is again to maximize the expected advantage, with a nice thing that we don't need any hard constraints here, because they use so-called differentiable trust region layers, which implicitly are there to satisfy the constraints. So basically, given a mean and a covariance, they map it back so that they that they satisfy some constraints, like the KL constraint in the previous example. And then they showed on this table tennis example that again these black box algorithms work a lot better, like with these reward functions, because again, like the reward function for this task consists of like minimizing the distance from the ball to the racket, minimizing the distance from the ball to the target location. You never know when in your in the trajectory this will actually happen. So it's like a really like a trajectory based reward. And in this reward, in this learning curve, the dashed lines basically indicate when a policy was able to hit the ball, and the solid lines indicate when the agent was actually able to place the ball near the target. And only this black box reinforcement learning with like this trust region layers was able to actually do this in this case. So if we again have a look, like classic PPO is only able to sometimes hit the ball, but it's never really able to put the ball near the target location. The next concept, or like a more complicated concept or more complex concept, is to learn multiple solutions for a given context. And for example, again, in the table tennis example, given like the same context of incoming ball and maybe target location, we want actually to learn different behaviors. For example, we want to have like a stroke that goes from left to right, or like something that just goes forward, or uses the backhand of the racket. And these kind of policies can be described by mixtures of experts policy. So again, we have some weight. We want some weights given a context, but this is then a composition of like kind of a mixture model of a gating policy that assigns a so-called expert to a given context, and then it's again each expert then is again a movement primitive, for example. So, but instead of just having like one behavior given a context, it's several. So and the algorithm that they were proposing involved some kind of like curriculum learning, where if we where the idea is to generate actually preferable context for learning. So starting with like generating your own like simple context to learn like more simpler behaviors, and then go towards more complex behaviors. And they do this by introducing like a learned context distribution rho. And if we again have a look at this this figure here, like during training, we actually sample context from this learned distribution, execute, then create or like obtain like the weight vector for this context, execute it and optimize the parameters. And the interesting part is that this learned distribution is part of the objective function, and then goes towards the actual task distribution by using like this this KL divergence here, and the entropy term ensures that that we actually learn, or that they actually learn diverse behaviors. So to summarize, different algorithms that we have seen for now is so based on the problem setting, we have like different methods which differ in like in complexity, but also like in in the task that they can solve. So in the non-contextual case that we had in the beginning, we can just have like black box methods such as more or CMAES. If we have contextual problems, they can be also solved with linear methods, with like an extension of more, and also with these non-linear model methods like this black box reinforcement learning algorithm that I was showing, with that are mapping from context to movement primitives using neural networks. For diverse skill learning, there's like there's also linear mixture of expert models, but the more interesting ones are the ones that use like the nonlinear mapping with neural networks. If we go back to the original slide with like this action exploration here, so if we compare step-based exploration, episode-based exploration, so step-based exploration happens like at each time step for each action, while episode-based exploration happens like before the episode actually. So we actually explore in the space of parameters, which means that in the step-based case, we actually get quite a lot of data points, because each transition, like state, action, reward, next state, is a data point, while in episode-based reinforcement learning, only a whole trajectory basically is a data point. So the question is, can we also formulate episode-based reinforcement learning algorithms that are a little bit more sample efficient than just like this pure episode-based reinforcement learning, but still have this nice feature of like efficient or like smooth exploration? And actually, there is like one method, like it was like recently published. I think it's in this year's ICRA, I think, which takes, instead of whole trajectories, trajectory segments, and uses these segments as data points. So instead of defining the advantage in terms of the weight vector and the whole trajectory, they define it in terms of like different states at different time points, and the actions taken like during this part, and also the likelihood of trajectory parts instead of the likelihood of the whole trajectory, basically. And they then evaluated this on this meta world task suite. So meta world basically provides a suite of like robot manipulation tasks, and this is like an aggregate result over 50 tasks of and basically they show that they are on par, or they can actually outperform like the usual PPO soft actor critic based algorithms in this task. To conclude, episodic or episode-based reinforcement learning can be better suited for robotics, because we have like this smooth exploration compared to the step-based approach. It's also well suited for problems where the reward is sparse, so sparse in time, and also maybe even non-Markovian due to like the nature of the task. The policy search objective is more robust than just like maximizing classical maximizers such as CMAS. And we can like find some trade-offs between expressiveness and complexity depending on the problem setting, basically. One thing that we have to keep in mind, though, is nothing comes for free, so that also like this movement primitive design may need some domain knowledge sometimes and some tuning. For example, like you have to choose the number of basis functions. You have to maybe find the scale correctly of the search distribution. So like it comes with other challenges as well. And that's actually it. So here's the references.